Welcome to this video on the photoelectric effect, a phenomenon that helped demystify light and matter and ushered in the quantum revolution. The photoelectric effect is when electrons are emitted from a metal surface after being illuminated with electromagnetic radiation of sufficient frequency. If the light frequency is high enough, current flows. If not, or if a barrier blocks the radiation, emission stops completely. Experiments with an electroscope provided key proof. UV light on a negatively charged plate caused the leaf divergence to decrease, showing electrons were repelled. If the UV light was blocked by glass, the emission halted, confirming the importance of UV radiation. The classical wave theory failed to explain these observations. Max Planck proposed a shift. Light energy propagates as discrete packets called quanta, or photons. This led to the fundamental relationship, E equals hf, linking energy and frequency. Think of the process as an energy toll booth. The incoming photon's energy, hf, must exceed the metal's work function, W_O, which is the minimum energy required to dislodge an electron. Any excess energy becomes the electron's kinetic energy. Einstein's photoelectric equation summarizes this. Photon energy, hf, equals the work function, W_O, plus the maximum kinetic energy gained by the electron, 1/2 m_ev squared. Three main factors govern emission: the intensity of radiation, which controls the quantity of ejected electrons, the energy or frequency, which controls the speed, and the type of metal, which determines the absolute frequency threshold. In the lab, intensity is manipulated by adjusting the distance between the light source and the photocell. Decreasing the distance increases the intensity, causing more photoelectrons to be emitted per second, which increases the current. To measure the exact speed of the electrons, we use the stopping potential. A reversed battery opposes the electron ejection. The voltage needed to stop the fastest electron is the stopping potential, reflecting the electron's kinetic energy. Here is an application scenario for finding the threshold frequency. First, convert the work function to standard joules. Then, apply the formula F_O equals W_O over H to calculate the threshold frequency, which in this case is 7.72 times 10 to the 14 Hertz. In the potassium case study, we calculate the work function, the maximum kinetic energy, and finally, the source frequency of the incident radiation using Einstein's equation. This scenario demonstrates finding the threshold frequency from wavelength, converting the work function to electron volts, and calculating the maximum speed of the emitted electrons. The complete photoelectric system balances the incident radiation energy, the material's threshold, and the resulting electron emission, all captured by the foundational equation. hf equals W_O plus 1/2 m_ev squared.